My name is AJ Buniskis, and today I would like to talk about how calculus can be used in football and how it can be the difference between a touchdown and an incomplete pass. So, calculus is a branch of mathematics that studies change. Typically it deals with continuous change. And knowing that calculus is applied in our everyday activities, but it's not something that we always think about. Like we don't think that we're using calculus. When we're driving. Um, that deals with calculus, but we don't think about that. Uh, in the military, they use calculus with like bullet speed, bullet trajectory, um, and other things like finance, economics, stuff like that. And in sports, right there's a picture of a golfer, and that all that deals with calculus. But today, specifically, I want to talk about how it is used in football. So, how calculus can be applied in football. Um, and quarterbacks throw, uh, it deals with calculus a lot. It's honestly the one part of this like whole entire project that I did find calculus being applied to a lot, because it follows the path of a projectile. We can optimize a throw by finding that ideal angle that maximizes distance or accuracy. Um, Between plays, between throws, quarterbacks adjust this unconsciously. So when they miss a receiver on one play, they can go right back to it by tweaking a little bit, uh, like dealing with their velocity or maybe the angle that they're throwing the ball, or even the distance that they're throwing the ball. And another way that calculus can be used in football is calculating a receiver's speed and their acceleration, with the first derivative of position, with the first derivative position over time being their velocity, and the second derivative of position over time being their acceleration. So, in order to calculate a receiver's acceleration, the formula would be acceleration equals dv over dt, a being acceleration, dv being the change in velocity, and dt being the change in time. And to calculate the angle of which the quarterback threw the ball, projectile motion, um, that equation would be r equals v to the second power times sine 2 theta all over gravity. But since we would be solving for the angle, meaning we would be solving for theta, you would have to rearrange that um, equation in a sense to where we are solving for theta. And as you can see there, that's what all the variables in this equation means. And I'll show how all that is applied and how I ended up getting that equation instead of the regular projectile equation. So here's my example of I'm going to show you two examples. This is play one, where you can see that this ball is incomplete and the ball is a little bit out of reach of the receiver right there. Um, right here is the math I did for the acceleration and the velocity of the receiver. It took him about 3.53 seconds to run a distance of 22 yards, and I decided to do this in feet, so I said 66 feet. And although it's not the ideal uh, derivative, it is still showing change of um, a change of speed, or a change in distance over time. So what I ended up getting is that his acceleration on this play would be 5.30 feet per second squared, uh, with delta v being a change in velocity, which is the final velocity minus the initial velocity, which the initial velocity would be zero in this case since he's at a standstill, um, and then t or delta t being the time it took to get there. So ended up getting 5.30 feet per second squared. And now here's the math on the quarterback's throw. So the quarterback threw the ball 31 yards, which would be 93 feet, and the ball took 1.68 seconds till the receiver touched the ball. So that would be kind of where the ball stops. So the velocity of that throw would be 55.35 feet per second. Now, up top right here is where I kind of switched this original projectile motion formula into this right here, or sorry, this right here to get the angle. And knowing that gravity in feet is 32.17 feet per second squared, and the range was 93 feet, and the velocity was 55.35 or 357 feet per second. That's how I ended up, or you just plug that in, and that's how I ended up getting his uh, angle being 38.75. Now, that's all for the play one, where it was an incomplete pass. This video right here, the second play, is actually the play right after that first play. So that everything football is the same. The defense ran the same play, the offense ran the same play. Everything was the same dealing with football. And as you can see here, this ball is caught. And in the video, it's not playing the sound, but in the video, the announcer even goes, "That one was a little easier now, wasn't it?" So what I found was that the receiver actually ran like a very similar speed to the one that he did in the first play. He ran 66 feet in 3.55 seconds, so he was just a little bit slower, and I'll explain why that is in my conclusion. And his acceleration ended up being 5.24 feet per second squared. And now the angle which he threw the ball was roughly the same as well as the first play, but his velocity of the ball was a little bit different. He threw the ball only 84 feet this time, and the ball got there in roughly around 1.6 seconds. I do want to go ahead and say that these are like rough estimates. It was kind of hard, not hard, but I tried my best trying to just like slow down the video as much as I can, trying to get a precise, as precise as I can of time when it came to the ball getting to the receiver from the quarterback's hands. And the angle in which he threw it at was 39.32 degrees, roughly the same as the first throw. And because of all this, what the conclusion is that it makes sense to me, or it makes sense as to why the receiver had to speed up at the end of play one. The ball was overthrown, as we can see. If we went back to the first play, that he did have to kind of like get to that ball a little bit quicker. I mean, that's football. That's what happens whenever the ball is slightly overthrown. But because the angle of the throw was the same kind of on both plays, that kind of just leads us to know that the velocity was the factor in which determined whether or not that pass was going to be completed. So the quarterback then knows that he has to tweak something in his throw a little bit. There has to be something that has to change. And he changed how hard he threw that football. And because he threw the ball slightly, a little bit less hard, the receiver, who ran just about the same speed, was actually able to come down with the football. And that, to me, is how calculus can be applied to football. And as a football coach, this is something that, as a receivers coach, honestly, this is something that, I could look at, knowing like maybe this receiver shouldn't run this because he's not as fast and the quarterback throws a hard ball, stuff like that. So that's how calculus can be applied to my everyday use in football.